Alright, so here's a problem that goes with the last one from 5.1, part 1. It says that about 55% of high school students participate. They're actually athletes. They're students and athletes. They're students first. Go on. To play in the NCAA, right? So that is they play in college, right? Well, you know, I wasn't showing it love today. So we want to know what percent of high school students play a sport in high school and go on to play a sport in the NCAA. Sorry, I'm going to be not grammatically correct and just buzz through this as I can. Okay, so. All right. So what do we know? We know probability of, we're going to call it probability high school, is 0.55. And we also know that the probability of NCAA given, right, that's what they've told us there, given that they played in high school. Is equal to 0.5, right? I'm sorry, 0.05 is what you mean to say. Okay. So, we're looking for the probability that they played a high school sport and played in the NCAA. All we need are these probabilities here, not necessarily the problem. If you need to write any of that down still, or you good? Okay. So we have our formula, right? We have a rule that tells us that this is going to be probability high school intersect NCAA, which should be equal to probability of high school times the probability of high school given. My bad, I did it wrong. Sorry. We want probability NCAA given high school. Fantastic. Well, you have all of those things, right? So we're just really following a formula right now. Which is why I'm staring at my book, because if I was doing this, I would put in the formula. I don't have these formulas memorized. And these formulas will be on your formula sheet that you get for your exam. So that's going to be 0.55 times 0.05. Which turns out to be fantastic. Cool. So almost 3% of high school students will play a sport in high school and in the NCAA. And does that imply that some students don't play a sport in high school and play in the NCAA? That's crazy. You got to be pretty beastly if you believe that, right? Yeah, that's right. There's both, right? Yeah. There's maybe some kids that are homeschooled and live someplace far away, but they, huh? All right, so let's do something different now. Hey, it turns out that Shannon, she hits her snooze bar. 60% of the time, which is unusual because I hit snooze 100% of the time. Maybe 99.9. It's very rare, but sometimes that goes off and I just say, yeah.
Is that
I didn't do it.
Okay, so if she doesn't hit the snooze bar, all right, so if she hits it, there is only 70% chance.
what? Oh, that's 1%. I don't think
Dang it. So, on a randomly chosen day, what is the probability she's late? All right, let's do this. Okay. So, You imagine this scenario in your mind, right? Shannon wakes up. Either she hits the snooze bar or she doesn't, right? Pretty much. That's the first event that occurs, right? So she wakes up. There's a 60% chance that she. And let's go ahead and express these as a proportion instead, or as a decimal. And then there's a 40% chance that she doesn't, right? Okay, so if she hits the snooze bar, two things happen. She makes it to class on time or she doesn't, right? So we'll say on time. Huh? And this one is not on time.
Not
Alright. What happens? It says that if she hits it, there's a 70% chance that she's on time, right? Which means that there is a 30% chance that she is not on time. Our other scenario is she does not hit the snooze button, right? Which happens 40% of the time. Sorry, I'm going to go ahead and... It says in the problem that if she doesn't hit the snooze bar, she is on time 90% of the time, right? But she is not on time 10% of the time, right? We're just using the complement rule on each of those. So now we can find all of these different probabilities, right? So in order to calculate this probability that you hit the snooze button and are on time, we have to introduce a formula, okay? Which in your book is introduced after this, but used during this time. That messed me up a little bit. I was wondering if they were actually doing that or not because it wasn't logical. So we're gonna have to actually make a little side trip and talk about independent events. So it turns out that hitting the snooze button is independent of being on time, right? The fact that I hit the snooze button, it doesn't change this probability, right? There are two different possibilities that come off. Now we're going to talk about independent events a lot more in depth, but it turns out that what we're going to use is the idea that if the two events are independent, then the probability of A and B is going to be equal to the probability of A times the probability of B. So that's what we're using right now. And the reason why that is because in this case, the probability of A given B, right, or the probability that you are on time given you snooze, okay, I got that 2 seconds. is just equal to the probability in other words, the probability that you are on time, given you hit the snooze button, is just the same as the probability that you're on time here, right? In this particular case. So that's what's happening. So we're actually using the formula for conditional probability, but it happens to be the case that this piece of it, right? Because we have this formula that says that the probability of A and B, or A intersects B, is equal to the probability of A times the probability of B given A, right? But in this case, the probability of B given A is equal to the probability of B. So then this is going to become probability of A intersects B is going to be equal to probability of A. I didn't need a multiplication sign. Yeah, probability of A times the probability of B. It just tripped me up because that needs to be explained before we actually make these calculations. So it's really nice because when these two events are independent, we'll talk more about independence after we finish this problem. You can just multiply the probabilities. So I am going to erase this because I don't want to scroll up. You probably have room on your paper. So this one then is going to be 0.6 times 0.7, which is 0.42. This one is going to be 0.6 times 0.3, which is going to be 0.18. This one is going to be 0.4 times 0.9, 0.36. And this one will be 0.4 times 0.1. All right, so now we can answer the question, right? Because the idea is that there are two outcomes that satisfy what we're looking for. We're looking for the probability that she is late. So this is not on time, and this is also not on time, right? So what we run into is the probability that she hits snooze and is not on time, or she doesn't hit snooze or is on time, right? So we want the probability snooze and late. Right? Or not snooze and late, right? So that's just going to be, we're going to go ahead and add those probabilities, right? So that would be the probability of snooze and late plus the probability of not snooze and late. Sorry, that's really hard to read. All we're going to do is be adding those two probabilities then, right? So we would have 0.18 plus 0.04 Oh. So that's 0 point. We have answered the question. Feel I feel like it was just so weird to not talk about independence before we did that. Well, let's go ahead and do another one. All right. Yay, snooze bar. Hey. I really like the example that they actually used in your book. It's pretty cool. It's the last thing we want from our table is we would like to know this probability. So see, given that the person describes his grades as good, what is the probability that he or she is a heavy user of media? Okay. So we're looking at the probability heavy user given good grades. Boom. Okay. So what is that going to be equal to? Let's go ahead and let's see. Can we use I would like to use oh well, we're just going to do this. So that's probability heavy user. And good grades. Divided by the probability that you have good grades. Boom shakalaka. So, heavy user and good grades, where do we find that on our table? Okay. All right. So we have heavy user and your grades was this is our probability that they're a heavy user. A hard time saying that over and over again. A heavy user of social media, and they have good grades. Okay, cool. So we'll plug that bad boy in. And probability that they have good grades.
Then we calculate.
Yeah, oh yeah, because we did calculate probability of grades, right?
Yeah.
So when you get a table like this, when you get a problem like this, I'm sorry, we have to use a tree on the AP exam. We'll ask you for a probability like that, where you have to do a number of different calculations to get to the end. Right? It's usually not really straightforward. So, and this is P equals to tenable with these probabilities. One of the favorite questions is talking about a false positive from some sort of a test, right? So it turns out that one that I used to use for a while, and I couldn't find it, but this one's pretty good, is it turns out that you're right, it's possible, it actually isn't super uncommon, for a person to take a test for, say, HIV and get what's called a false positive. So you get a test, you get an HIV test, and you test positive for HIV. Your world comes crashing down. Yeah. It's actually a lot less. You would think it's uncommon, but it's actually more common than you think. I have no idea. But that's why you go back and get a second test, because after you get that second test, the probability of it being wrong twice is much smaller than the probability of it being wrong once. So, let's get into that. Alright, so this is way more interesting. Okay, so you take a test. It turns out that the probability that it's correct so Oh my gosh, my brain's not working right now. My brain decided to shut down. So another number that we would really like to know, right? And these drug companies that make these tests have them, and it turns out that the other thing happens too, and it's a good probability to have. So we're only going to get a piece of the picture with this, because the other side of the coin is that a person who's actually pregnant doesn't test positive, right? So we have to assume that the person taking this test, I guess we'll assume that the person taking this test isn't pregnant. Yeah. Yeah, we do have to split it, so we need more information. Hold on. Okay, so we got a test that tests whether a patient has contracted HIV. It's positive if it indicates that HIV is present in the blood sample. It's negative if it doesn't indicate. Okay, obviously. It measures levels of antibodies in the blood. It doesn't always indicate a correct result because of that. All right. So, staff at a testing lab, they did this test of 500 blood samples known to contain HIV. the LSL was positive for 489 of those blood samples and negative for the other 11 samples. As a part of the same training program, the staff also applied the LSL to 500 other blood samples known not to contain HIV. LSL was positive for 37 of those blood samples and negative for the other 463 samples. Okay, so what is the probability that it's positive when it's applied to a blood sample that does not contain HIV? So what do we know? We don't need any of this stuff in this top paragraph. What we need is all this stuff. All right, so we're looking for the probability. For you. All right, so we're going to look at the blood samples examined in the training program that provided positive ELISA results for HIV. What proportion actually contained HIV? All right. So we're looking at our we got to keep these numbers in mind. I'll get this out of the way. So we have 500, right, that actually contain HIV, right? For sure. Yeah? Okay. We're going to have, let's see, negative for 463. Okay. I need to write stuff down. Not that. All right. Okay, so let's look at positives. How many positives were there? We had a total of 463 plus 37 positives. I don't feel like no, it's already 463 negatives. Oh, it was negative? Okay. Oh, 37 were positive. Okay, sorry. So we had 37 positives, and then up here, okay, there we go, 489. My bad. That's the wrong number. All right. Thank you. All right, so those were our total positives, right? So we know that this guy, so we're going to call this probability HIV. We know that that's our samples. That's our sample space, right? Okay. Now we need to figure out which ones actually contain HIV? Yeah, 489. All right, I believe that's good. That's actually not as tricky as. Okay. Yeah, that's it. That's the proportion of all positive results that actually contained HIV.
This was on the AP test.
Yeah, 2009 AP.
So
It was one of the. So you get 6 free response questions. 5 of them are shorter. This would be one of the 5. The 6th one, the last one, is really long. No, yeah, and it so usually number 6 on your free response, they're gonna give you data. Instead of just giving you numbers already worked out, you're actually gonna have to use the data to create some statistics. Alright, so let's make our segue into talking about independence, and then we're done with chapter 5 lecture-y stuff. And we'll do more work. I have some probability problems for us to work on, and then of course the homework assignment. So, in your book, number 1, in your book there's a definition of independent events. So check it out. Events are independent if one event occurring doesn't change the probability of another event, right? So another event. I was gonna add some element of them being. It's not essential. All right. So we can test this. There's an example of it in the book where we have, and I'm just gonna actually use this one, where you have your dominant hand. We're using a two-way table for this. Alright, here we go. Alright, so we would like to know, are the events male and left-handed independent, okay? So what's another way to say that? Right? How are the events male and left-handed? Are the events male and left-handed independent? In other words, does the fact that a person's gender, essentially, affect the probability of whether they are male or female, or whether what. I'm gonna say it's probably pretty good. No. What does a person's gender affect the probability that they are left-handed or right-handed? That's what I want. All right. So, in other words, is there a higher or a lower probability of being right or left-handed for males or for females, right? And we're going to be able to determine that from this two-way table. So, okay. Yeah. Poke your head through there. Huh? Oh, thank you. Okay. All right. So let's do probability left-handed given male, and let's compare that to the probability of. So we want to know, are these two things equal? Left-handed given female, right? Cool. All right. So, probability that a person is left-handed, period, is going to be 10 out of 100, right? Okay, left-handed given male. So we have 7 of those, right, out of 46. Those two guys are not the same, right? And therefore, so because of that, they are not independent. Does that make sense? All right, guys. I've done all the stand-up teaching that I can do for chapter 5. Now let's work together and learn. Yay!